So we're talking about polar coordinates some more today. Today we eased into it yesterday. Now we're going in this direction. We're going to be converting equations back and forth from polar to rectangular. So keep in mind the same tools that we've always been using all along, not just yesterday, but like all along in life. X is r cosine theta, y is r sine theta, and remember that like by definition of what we mean by r, it's x squared plus y squared equals r squared by the Pythagorean theorem, or the equation of a circle, or the distance formula, whatever you want to call that. Okay. So let's, before we actually do this, I'm going to ask us to plot this just together, you and me, and then we'll do some algebra with it too. I forget whether they make you do one of these in the homework too, plot a few points?
Yeah. Yes.
Okay, so let's actually do this same one here, similar to your homework. R equals 3 cosecant theta. Let's try and get at least a rough picture of this over here. So I'm going to, R equals 3 cosecant theta. That's 3 over sine theta, if you prefer. And we'll just build like a little table of values. And we'll plot it as best we can. Okay, so here we go. We'll just leave that off. So if theta is, what's a good angle? I don't know. 0, sure. Okay, if theta is 0, what do we get? That's inconvenient. Okay. What if we get let's I don't know, pi over 4? What's 3 over the sine of pi over 4? Sine of pi over 4 is 1 over root 2, so 3 times root 2, I guess, right? Right? Did someone approximate that for us? Can you calculate it real quick? Can you get that? 3 times the square root of 2 help us out here. Let's go to pi over 2. What do you get? 3. What about 3 pi over 4? Yep, we'll get the same thing as over there. What about pi? Undefined again. What about 5 pi over 4?
Negative 3 over 2.
Yeah, it'll be like we did here, negative 3 root 2. It'll be 3 over negative 1 over root 2, I guess. What about negative, oh, what about 3 pi? 3 pi over 2. Now we're down here. Okay. So let's start plotting some of these here and see what we get. So 1, 2, 3. If we're in the 0 direction, the way we plot in polar is we kind of start sweeping around. 0, what do we get? Nothing. Pi over 4, what do we get? Well, we're approximately, what should be 4.2 units out? Yep. So 4.2 units out is, I mean, this is 4 and change. We're like really doing a great polar grid. We would say it's like right here-ish, right? Is that about 4 units from the origin along that diagonal line? Sure, thank you. Okay. All right, so there, we got that one. Pi over 2. So now, as we're sweeping, we're going 0, pi over 4, pi over 2, 3 units away. If we're in the pi over 2 direction, we're 3 units away. So we're doing well. 3 root 2. We're in this direction here. 3 pi over 4. And we're going that same distance out there. Pi, we get nothing. 5 pi over 4. Now we're pointing in this direction. And we go 3 root 2 units. Oh, wait. Backwards. So we're actually here again, aren't we? So these actually land on top of each other, don't they? Right? 3 pi over 2, where are we? Oh, okay, what 3 pi over 2 is, we're sweeping here, right? 3 pi over 2 is, now we're finally here. We're going to walk 3 units, oh wait, backwards. To here again. Yeah? It doesn't seem like we're getting more points here. This is just like, we keep hitting these same points. We're not down here ever. Okay. Let's just store that up in our hearts. Let's actually go over here now and do some algebra. So over here we get r equals 3 over sine theta. Now, trying to, as best as we can, create situations where we see these things. What might you be dying to do here? Multiply both sides by what?
R.
Yeah. So r sine theta equals 3. What's this then? Another name for? So, okay, so I guess maybe all is clear. We were all a little bit in the dark a minute ago because we looked at this and we were like, what is going on? Undefined? What's 3 root 2? Oh, this is just the line. Y equals 3. It's also clear now. Okay. All right. So the algebra brings a lot of light here, doesn't it? Okay. So we can convert back and forth here. If you'd like to see your calculator graph this line in polar mode, just go to your mode on your calculator and select polar. Polar mode. When you go to your y equals menu now, or when you go to your y equals button, it won't say y equals y1, y2. It'll say r1, r2, r3, etc. equals. And when you push your xt theta n button, it will just already be ready. It'll be a theta for you. Okay. So try typing, I don't know, something in like 3 divided by sine theta, and graph that and see if you don't get a line. Okay. The default, by the way, just like in parametric mode, when you're going to window, you have control over x and y, mins and maxes and stuff like that. You picking up what we're doing? Okay. You also have control over your theta min, theta max, and theta step. So if you go to your window, the default is probably 0 to 2 pi right now, I'm guessing. So play around. Do you have confidence? I just would like you to participate. When you're ready and you're having fun with this polar mode in your calculator, try graphing this one, 2. 4 times cosine theta. Try graphing that one. You don't need a cover. Help each other out with the calculator here. Anyone see this yet? What do you guess that this is? Yeah, we can do zoom square on that. Zoom square. All right, so what do you see? What do you think it is? Did you do zoom square? Hit zoom and then hit square, which reproportions the x and y axis to be the same scale. You should be getting a picture like this. What do you suppose it is? Be more specific. Is the circle of radius what? Centered where? What does it look like?
Radius of circle.
So maybe you already have a hunch as to what the rectangular form for this equation would be. And by the way, before we ever graphed this, you might not have known that you wouldn't have expected this maybe, but you graphed it. It does seem to be a circle. Let's see if we can convince ourselves, just like on the last one here, algebraically, see if we can get there too. So let's start with this equation, and again, let's apply like wishful thinking, right? So again, we're trying to generate for ourselves circumstances that like just give us. What do we like? We love to see r cosine theta. We love to see r sine theta. We love to see x squared plus y squared equals r squared, right? So can we create for ourselves that situation? We love cosine theta, but what do we love more? From the previous page? We love what? We love cosine theta, but we'd like to see r cosine theta. And if you want something in life, guys,
make it happen.
Make it happen. What do you want? An r there? What do you want to do on both sides? I would like to multiply by r. So So now let's just play the substitution game. What's r squared? What's another name for r squared? From the previous page.
R cosine theta plus.
Or how about x squared plus y squared? And then r cosine theta is better known as x. So have we converted this to rectangular coordinates? I think we have. Now, it's maybe not as obvious as you'd like it to be in terms of like describing the thing you said it was. So maybe we multiply, or we move this 4x over here. And then we might complete the square by adding what? And does this seem like what you expected a little more? This is x minus 2 squared plus y squared equals 4. Is that a circle centered?
Oh, yeah.
Is that more obviously now a circle of radius 2 centered at 2, 0? So I mean, I think to answer this question, convert to rectangular coordinates, I think we've done it here. But just because I think we all wanted a little more clarity and connection on this situation, we wanted to go to here maybe just for fun. But I think this is a fine answer to the question, the first one. All right, let's go the other way too. So here, I might multiply things out. First, this is another what? That's right, circle. Good job. Okay. Let's multiply stuff out. You could make the substitutions now or later. It doesn't matter. So what do we get? X squared plus 8x plus 16. Y squared minus 6y plus 9. What do you see? Anything nice happening? Yeah, certainly x squared plus y squared is nice. That part will be r squared. So we'll use that. We also get an 8x and a minus 6y. And the 16 and 9 and 25. Yeah, that's going pretty well for us. So this is r squared. I don't know, let's just make our substitutions. X is also known as r cosine theta, and y is known as r sine theta. So we're doing pretty well. In fact, if you wanted to, we could even solve this maybe for, we could even maybe solve this for r, even. That would be pretty cool. Now, since r equals 0 is entailed by this solution, we can divide through by 6, by r. So there will be a time when this is 0, so I think we're okay in terms of dividing through by r. So I think that's a that's a good place to leave it. I mean, could you graph that on your calculator? Sure, feel free to put that in R1 on your calculator. You can graph it and see what it looks like. It'll be a circle centered at -4, +3, radius 5. One thing you could do if you wanted to go a little further with this, just for fun, right? Just for fun. You could take this right side and re-express it in ways that we did in first semester. Do you remember this? This is a linear combination of sine and cosine. Remember this? You could write this on the right side. You could write it if you could come up with it in the form like something times cosine of theta minus something. And that might make what angle this is rotated at more obvious too. I don't know. It'd be an extra little fun thing to do. Okay, but that's fine. We'll leave it there. This looks like a barrel latch right here. Again, let's think about what's convenient for us. What's really nice for us is we do like cosines and sines of theta, and in particular r cosine theta and r sine theta. We love seeing those things. But you know what we don't really love seeing? Cosines of 3 theta. So we need to get this in a form that so that we have cosines and sines of just theta. Yeah, we gotta go there. We'll put candy on this one. Someone say it out. Cosine of A plus B is what again? Shout it out. What did you have?
Cosine B minus sine A sine B.
You were the most vociferous, so you both get it.
Yay.
What? What did you say that? Huh? Okay.
Cosine of J plus
That was right.
times
Thank you. Okay. All right, 6. What they said: 6 cosine this, cosine that, minus sine this, sine that. All right, wonderful. Okay, we have available now a second. You guys are out of the running though. A second candy opportunity. What's the cosine of 2 theta? What'd you say, Brandon?
What?
Nope, not
Cosine
sorry. Josh, wait,
Cosine
Josh.
squared theta minus sine squared theta.
No, cosine squared plus sine squared. No, wait, no.
Josh said.
Oh,
Minus sine, minus
Cosine
sine.
squared minus sine.
yeah. I thought I got it wrong.
I believed in you.
Thank you.
Okay.
No.
What about sine of 2 theta?
No, 2 cosine and 2 cosine.
2 sine
theta.
No,
No,
wait.
it's 2 cosine and then sine.
SMH giving away the answers.
No, hey. No, I said it. But then Katie was like,
Oh yeah.
All right, yeah, we need it. Never forget. Never forget. All right. Whoa. Come back to order. I know that was exciting. So, it's good for you to remember these things. I don't know what just happened there, but we'll go with it. Okay. I don't know. Just ignore that. Okay, well, we're having fun here. Okay, so we get 6 cosine cubed minus, sine. How many sine squared thetas do we have? We have -1 here and another -2 sine squared cosine thetas here. So together that's 3 of them, -3 of them. Yeah, right. Or maybe some of you, I should have really given you candy for this. Anyone remember the cosine triple angle identity? Boom, and then you should write that down. Oh yeah, of course, cosine cubed minus 3 sine squared.
back in my hand.
NBD. Okay. No, we didn't memorize that one, but one could, I guess. Okay. Good. What do you got here? So now, again, I think we're finally in the position where we have cosines and sines of just theta, but we want to play the game of wishful thinking. Can we replace some of these with r's? I mean, can we get some r's in there too? Can we get this to be an r cosine theta cubed? Keep in mind that this is cosine theta, cosine theta, cosine theta. So what we really need to see is r cosine theta, r cosine theta, r cosine theta. So we need to multiply by r, and another r, and another r. We need to multiply this entire equation through by r cubed. Now, will that do the job over here too? We need 2 r's here and an r here. Because there are 3, we need an r to go with each of the cosines here.
What if it was like, how do you know it's the 3 cosine? Why not the 2 sine? Or the 1 cosine?
Yeah, we do. You're right. We call 18 r cubed. So let's verify that you're right. We didn't even talk about down over here. We should think about how many we need there. But I'm asking you both questions simultaneously. How many do you need here? How many do you need over here? The answer just happens to in both cases be r cubed, right? So over here we have r squared. That's what r to the 4th is. Over here we have 6 times r cosine cubed. And here we have, are you comfortable with this? R sine theta squared r cosine. I'm just moving those r's to where I'd like to see them. And now we're ready. We've really set ourselves up for success here. That's an r, sorry. This is an r cubed over here still, isn't it? Joy, you want to come hang out with us? You could come learn some pre-calculus.
No.
Come on. You might not have to. You might have to get notes later. You could get it all now for free. 7 minutes, you'll be able to do your homework then. Oh, yeah, sure. Yeah, it's been real. I'm hurt. R squared is x squared plus y squared. That thing squared. We get 6. What's that? X cubed minus 18. What is that? Y squared x. This is not the kind of thing that we're going to be solving for y, friends, but that's good right there, okay? Now, have you graphed this yet on your calculator? Good, I hope not, because you're in for a very delightful surprise. Type that in and see what you see. You're going to like it. It's pretty. It's pretty. Isn't that nice? Wait, that's a little long. Oh yeah, you're playing around.
Now I can actually see why someone actually said it.
Did you get this nice curve? If you have I feel like, I don't know, maybe some modern calculators can type this in. If you type this in Desmos, you type this in, or this, you'll get the same picture, okay? Alright. Speaking of beauty or the lack thereof, let's take a look at this guy here. How do we convert this? Really, this last example, my friends, is a lesson in not everything is beautiful in terms of well, we just want to give a word of caution here. Okay, so we'll put a little danger sign here. Okay.
Oh wow! Wow.
Yeah. I got you.
Wow.
That's so cool.
Isn't that like the Fibonacci thing you remember?
Okay.
Yeah, it looks like that.
That's a good danger sign.
It's a danger sign. Okay, because look at how this is going to go. You're not going to like this.
Okay.
No one liked this, but we're gonna see. The thing is, like we said, betas all alone, not really nice, right? We like cosine betas. We like, so this is not super nice. I don't know. We could maybe do like x squared plus y squared. Take the square root or something for r. We could on theta. We could say like, I don't know. This is terrible. Tan inverse of y over x, but we know that's a lie. Squared. This is a mess. The reason is that this looks like this. And writing rectangular coordinates for this is not super nice. Let me pull up Desmos to show you how this goes here.
Spanish again. Oh my god.
So if you're in Desmos and you're doing this, I just typed in r equals theta squared. By the way, in Desmos you have the ability to do polar grid coordinates too if you want.
Wow.
Wow. That's so
So, so let's type in the thing I just typed in.
I didn't know what happened.
I mean, this is not pretty, Come on now. Come on now. All right. This is what we just said. There's like a sense in which we didn't lie, right? But there's also a great sense in which we're really not really capturing the spirit of this, okay? And the reason that tan inverse doesn't have, maybe we could take another square root here. All this garbage here. And maybe we could take the tangent of this side, I don't know. Maybe we can make up for our errors and our lost the years, the locusts of 18. Everything's fine. That's not too bad. We get an extra spiral there. But that's not too bad, actually. Maybe we could do better on these. But the point is, the ones that were at the front of our lesson today were all like very carefully chosen, weren't they? So that they would come out to be very nice things. Let's also do the one we were just doing a second ago. What was that? R equals 6? Doesn't matter. But, and let's just verify that that really does equal the same thing as the other thing we got. X squared, y squared, squared equals, help me out, remember 6. X cubed minus 18.
Y squared x.
Right? Beautiful. Desmos for the win. Okay, so homework number 2 tonight, please. Okay. At some point, we'll explore more of the graphical side of this and why these look as beautiful as they do. Like, oh, I don't know. Well, I would say Monday, but we have an ID problem on Monday, a test on Tuesday. So Wednesday, though, when we come back on Wednesday for this finally, and we come back to some of these discussions Wednesday and Thursday, we're going to do a lot with graphing. But right now, you're just playing around with the equations, converting. I think I gave you a couple extra problems on homework 2. Just look at the sheet and make sure you do them. And have a good weekend.